So last week we introduced networks, and the way to deliver data through networks is to use switching, where we have these special intermediate nodes, switches, that forward the traffic through the network. One part that we didn't talk about is how do we choose the path from source to destination. In our network we have the stations, the sources, the destinations, and inside the network we have the switching nodes. And our data from source to destination goes from one switching node to another, and eventually to the destination. The question that arises is, if we have multiple possible paths from source to destination, how do we choose the best path? And that's what this topic's about, routing. Routing is the process of finding the path, a route, from source to destination. How do we perform routing in switched networks? And you should find this reasonably simple to understand the concepts, because you see routing being applied in many other aspects, not just in computer networks. So we'll talk about what do we mean by routing and introduce some terminology. We'll talk about some very basic strategies for choosing the best path, or choosing a path. And then we'll finish with a simple example of a routing protocol, or a simplified routing protocol. This is the example switch network that we introduced last week. Just a very simple example where we have the switches in the middle and some stations that may want to communicate with each other on the outside. Routing is solving the problem, what path or route, they mean the same thing in this context, a path or a route, which path or route to take to get from source to destination. We said when we form a network, often we'll structure the network such that there are more than one path. To get from B to F, we can go along this path, that is this sequence of links, or an alternate path. So there are usually multiple possible paths to get from any source to destination. If we have more than one possible path, we need to choose a path, and that's what routing's about. So it's important in switch networks because it will impact upon the performance of our data transfer. Which path or route should be taken from source to destination? Well, the answer is easy. Choose the best path. But we need to define what do we mean by best, and how do we have an algorithm or a protocol that will calculate that for us. For a network, we don't want a human to have to calculate what is the best path. We'd like computers, and in fact, in most cases, the nodes themselves to calculate the best path. So we need some algorithms to do that. We'll use some simple examples, like on the previous slide, an example of 6 or 7 switching nodes. But remember, real networks may have hundreds of switching nodes. So hundreds, thousands of switching nodes. They're much more complex than the examples we see. There may be many possible paths, and just looking at the network and saying this is the best path is not possible. It's much more complex than that when you have large networks. That's why we need computer algorithms to calculate the best path for us. Routing is needed in both circuit switched and packet switched networks, so it applies to both. Both we need to choose a path. It's just that in this lecture and subsequent topics, we're going to focus mainly on packet switched networks, but the concepts also apply in circuit switched networks. So we need first two things. We need to define what do we mean by best. If I say choose the best path from source to destination, what do we mean by best? And then what algorithm would calculate that best path for us, so a routing algorithm. An example of routing is driving from one location to another. You want to drive from here, this campus, to the centre of Bangkok, go shopping somewhere in Bangkok. You need to drive along the roads to get there. How do you choose a path to get from here to Bangkok? Does anyone have an algorithm? If you had to drive, or you had to tell your friend, how do you drive from Bangkadi campus into the MBK at Bangkok? What would you tell them? You're eating. I won't interrupt your eating during my lecture. Any idea? Any idea of how would you choose the direction to take to get into Bangkok? Have you ever driven into Bangkok or been in the car with someone and directed them? Sorry? The shortest way. Shortest measured in what? Measured in what units? Less distance, so meters, kilometres. Okay, there's one approach. Choose the path, choose the set of roads that will travel the less distance in kilometres. So you calculate, before you drive, you calculate the exact kilometres to go from here to Bangkok on all the possible paths. I don't think you do calculate very precisely. But, okay, so there's what we say a metric. One metric for determining the best path, what is best, may be distance, say measured in driving in terms of metres or kilometres. We can have a similar metric for communication networks. So that's a metric, a way for determining best. How do you determine which of the multiple paths to drive that gives us the shortest distance? Do you know? So there are many roads to take. How do you know which one is the shortest distance? Shortest number of kilometres?
Use navigator.
Use the navigator. What does that do? What does the navigator do?
Find the shortest path.
Yes, that's what we want to do, find the shortest path, but how? Shortest in terms of metres or kilometres, but how do we do that? Or how do you do it? Or you could look on a map, and that's what your navigator does. Your navigator just looks on a computerised map and does some calculations. If you have a map to scale, you could, okay, measure this road, that's going to be 5 kilometres, then I'll turn left and that's another 3 kilometres, and so on. But of course you need to consider the other paths as well, and you need to do a reasonably complex calculation to consider all possible roads, which one is the shortest in terms of driving along each road. If you did it just by the way a bird would fly, a bird can fly not along the roads but direct, then it would be easy to determine the shortest distance. But of course we don't drive, or we have to drive on roads. So it's not so simple to even determine what is the shortest path to drive into Bangkok. But it's possible. How else may you determine which direction to take? You don't want to drive the shortest. What else may you do? How you normally go? What does that mean? That means you've been before. How did you go the first time? How did you choose that first path? So that relies on some previous knowledge. Lowest traffic. Go along the path that's going to avoid the traffic. How do you know where the traffic is? Experience. Listen on the radio, watch on an internet website that gives what's the latest congestion, where a traffic jam is. That is, you collect information before you choose the path. Information from other friends who may have driven there yesterday and know that there's a roadworks happening there. Information from the radio which says there's a traffic jam at this intersection. So importantly, you need to collect information about the status of the network, status of the roads, and then make a decision, say, to avoid congestion, so that you get a shortest path in terms of time. That's another important metric. Any other options of how you may choose to go drive into Bangkok? Fastest. Okay, so that's another thing about, all right, if you know the speeds that you can travel along roads, go along the roads which allow you to drive the fastest. Before we said the shortest distance, but that's not very effective if the shortest distance we can only travel at 20 kilometres per hour. If we had a longer distance but we could travel at 100 kilometres per hour, that may be better. Anything else? I've got no money. What do I do? Minimise my cost. Choose a path that avoids the tollway if I don't want to spend any money. So there's different metrics: distance, financial cost, time, congestion, and all of those come into play in terms of how do we choose the best path. The same with networks. There are different metrics for measuring what is best, and we need algorithms to calculate the best path, and we often need to collect information about the network to perform that calculation. The algorithms that calculate the best path, the requirements of such algorithms, some are obvious, the requirements are listed here. We need an algorithm that will give us the correct path. So a routing algorithm takes as input source, destination, returns as an output a path. That is the set of switching nodes to take. If I input a source and destination into my routing algorithm, as an output I'd like to get a path that gets me from that source to that intended destination. If I plug into my navigator for my car, I want to get into MBK in Bangkok, and it leads me on the path to Chiang Mai, that's not a good routing algorithm. That is, it needs to get me to the intended destination. That's rather obvious. Our routing algorithm needs to be correct. We'd like routing algorithms that are simple, easy to implement in software, cheap to implement. We'd like routing algorithms that are robust. Even if there are errors or problems in the network, our routing algorithm should be able to handle that. An example is that in our network, we have one path chosen. We discover that a link has failed along that path. There are errors along that path. Then our routing algorithm should be able to handle that and choose an alternate path that routes around that link. We'd like, as a competing requirement almost, a routing algorithm that gives us stable paths. My routing algorithm chooses a path from A to B, and I send some data along that path, and then 1 second later it chooses a path from A to B which is different, and I send my next amount of data along that different path, and it keeps changing over time. That would be an unstable algorithm and may cause problems with performance because some of our data will go along one path, some across a different path, that may impact upon the performance of that data. So oft we'd like to be able to have a routing algorithm that chooses paths which can handle changes in the network, errors, overload, but also not change the path too often. We'd like to choose the best paths, that's obvious. We need to define what is best. This is a harder one to give an example for. We'd like to choose paths which are fair between all stations. It could be that an algorithm chooses a path which makes it good for some nodes in the network, good performance for them, but makes it very bad for performance for other nodes. That would be unfair amongst the nodes. So ideally we'd like an algorithm that treats all the stations that need to send the data the same and chooses paths which gives equal performance for all those nodes. We'll see some examples of these as we go through specific strategies. The last one is efficiency. We're going to see that for routing we need to transmit data, control information through the network to calculate the paths. We'd like to minimize the amount of overhead. Processing overhead at nodes, so performing calculations, and transmission overhead. If we need to send some extra information to calculate a path, we'd like to minimize the amount that we have to send to keep the data transfer efficient. We've already mentioned some terminology, so let's maybe a little bit more formally list some terminology that we'll use. We talk of a link is a direct connection between two nodes in a network. A cable could be a wireless link. Generally, we call it a link. A path is a way between two nodes via one or more links. Let's use our example. This is an example network here. Forget about the numbers for a moment, but we see that we have 6 nodes, N1 to N6, and some links between the nodes. The arrows indicate links. So we have a link between two nodes, a direct connection between nodes. A path between nodes is a way to get from a path between a source and destination is some way to get from source to destination via one or more links. So a path from N1 to N6 is this path. It consists of 3 links, 1, 2, 3. We could write down the path on a piece of paper as start at N1, then to N4, then to N5, then to N6. So we could describe that path as just the set of nodes along the path. A path from N1 to N4 is this path. Another path from N1 to N4 is this. So this is just a path with one link. We have links, we have paths. What else do we have? Hops. The hops is the number of links we traverse to get from one node to another. To get from node 1 to node 6 along this path, we have 3 hops. 1, 2, 3. Or 3 links. We often refer to them as hops. We traverse 3 different links to get from source to destination. We have neighbour nodes. Neighbour nodes are the nodes which we have a direct connection to. Node 1 has 3 neighbours. 3. Node 1's neighbours are N2, N4 and N3. It has a direct connection to each of those 3 nodes. For the links, we usually assign a cost to those links, which is some value to indicate the cost of using that link. But when I say cost here, I don't necessarily mean financial cost. Cost in whatever unit we determine. The cost could be a measure of distance, meters. It could be a measure of financial cost. It could be some measure related to bandwidth, delay, many different factors we can measure. We generally call it a cost. And that's what the numbers on these links indicate, just as examples. The cost of using the link from N1 to N4 is 1 unit. In real cases, we need to define what the units are, whether this indicates delay in milliseconds, a financial cost in thousands of baht, or some other metric. And we may have links with different costs in different directions, as we illustrate here. The cost of sending data from N1 to N4 is 1 unit, but from sending from N4 to N1 is 7 units. That's possible. And in fact, we may have a link that only allows us to send in one direction. If we have a simplex link from N1 to N4, we would remove this arrow. That is, if we can only send data from N1 to N4, but not from N4 to N1, then we'd have to delete this arrow from this diagram. That's possible. The final terminology is that we have a topology. The topology is the arrangement of nodes and links. So this diagram is a topology of a network. It shows that we have 6 nodes. It shows which nodes are neighbours with which other nodes, and shows the costs of those links. If I remove this link, or this arrow, that would be a network with a different topology than the one with that arrow. If I remove this node, we have a different topology again. Just some terminology that we'll use when we talk about routing. Given that, our goal is normally to perform least cost routing. Choose the path with the least cost, where again cost can be whichever metric we specify, or even a combination of metrics. So if we have a topology of a network, and we know this topology, and if we know the costs of each of the links, then we can use an algorithm to find what is the least cost path from N1 to N6. Can someone find it? Your algorithm, you can use your brains and try them all, not so hard on this small network. Find the least cost path from N1 to N6. Anyone found the path? 1, 4, 5, 6. Okay. The least cost path in this topology is 1, 4, 5, 6. And the cost, and we treat the cost across a path as additive. That is, the cost to use that path is the summation of the cost of the links across that path. So 1 plus 1 plus 2, the cost is 4. So we could say that the path from N1 to N6, the path with least cost, is N1 to N4, N5, N6. And it has a cost, I'll just record the cost, the total cost of 4. How do you know that's the least cost path? I think many people found that. How do you know it's the least cost in this network? No other path have a lower cost. That is, you compared it against all other paths. You'd need to compare with this path, which you'd need to calculate in your head. Okay, this one has a cost of 4. This one has a cost of 5 plus 5 of 10. This one is 5 plus 5 is 10. That's not less. What about this one? And you try all the possible paths. So that's one way to determine the least cost path. Compare every possible path from that source to that destination. How many are there in this case? How many possible paths? Actually an infinite number, because if we go on a loop, we could end up there as well. There are many possible paths. It's not straightforward. All right? In a small network, we could calculate, assuming we don't go back over a link, we could calculate the number of paths. But there are many possible paths we could take in even this simple network. Now I give you a task which has 100 nodes, not just 6, like a real network. And if you need to look at that and determine what is the least cost path, you need to compare all possible paths. That's going to take you a long time. So in fact, there are algorithms that will calculate this for us efficiently. And what's the name of one of those algorithms? You studied this maybe in first year, possibly second year. Dr. Bunyarit may have taught you. Anyone remember? Bellman-Ford is one of them. Dijkstra Algorithm. When you talk about graphs, there are algorithms. Dijkstra's algorithm is an algorithm that will find the least cost path from one source to all possible destinations. So there are efficient algorithms that will do this calculation for us. What else can we say? So, some of the issues that we need to deal with, what metric or what performance criteria do we use to measure the least cost path? In this example, what does the cost represent? It can represent different factors, and in different networks, the organisation operating that network may choose a different metric. Someone who drives into Bangkok, someone may choose minimise the financial cost. Someone else minimise the distance in terms of kilometres. Someone else may choose do not travel through this area because there's someone who works there I don't like. So you may choose different metrics for choosing a path. What are some of those metrics? We'll list some examples of common metrics. Next thing we may need to consider is, when do we choose a path? We're not talking about cars, we're talking about getting data from a source to destination. Going back to switching, in datagram packet switching, we just send packets through the network. In virtual circuit packet switching, we first establish a connection and then send packets along the same path. At what point do we calculate the best path? Do we calculate when we build the network and leave it fixed? Or do we calculate before we send a packet? We'll see some examples of that. I think, in fact, the next slide gives some examples. Which nodes are responsible for selecting a path? We said that we need to know the path from N1 to N6, I need to know if node 1 needs to select that path, it needs to know the costs of all the links. And it needs to know about all the other links and all the other nodes. When you calculated the path, you looked at this diagram, you had knowledge of the nodes, the links, and the costs. And you calculated this is the least cost path. In our network, we need to somehow collect this information. If this node is in Thailand and these nodes are overseas, how does this one know that the cost from a node in Singapore to a node in Tokyo has a cost of 1? Somehow it needs to collect information about the network to make the decision. So what information do you collect? Which nodes provide this information about the topology, the costs, the current usage? And how often do we update that? Some examples of those issues are listed here. Some typical ways for measuring what is the best path, that is, what is the cost we assign to links, include number of hops. Remember, the hop is the traversal of a single link. What is the least cost path if we're using number of hops to get from node 1 to node 6? Our cost is now number of hops. What is the least cost path in this case? From N1 to N6. 136. 136. It takes 2 hops. 1 link, 2 links. 2 hops to get from source to destination. So if we said now, forget about the numbers. If you ignore all the numbers, choose the least cost path from node 1 to node 6 where the cost is the number of hops. That is, choose the path with the minimal number of hops. That's a common, very simple way to find the least cost path. It's very simple because you don't need to know that this link costs 7 in this direction and 1 in this direction. You just treat it, one link has a cost of 1. each link has a cost of 1. So if we were to use number of hops as a metric, you replace all the numbers with 1 and find the least cost path. And of course it will be this path because it has 2 hops. So that's one metric used in real routing. Financial cost may be a metric. The numbers on the diagram may represent some financial cost of using the link. That is, send our data through the internet that incurs the least cost. Because the network operators, they have to pay for connecting to other network operators. So the connection, say, from your local internet service provider, so you connect to your ISP may then connect to a national internet service provider. They may have to pay to send data, to send the traffic to that national provider. So that transfer of data has some financial cost involved. Therefore, it makes sense to try to minimize that cost. If you've got the choice, if an internet service provider has the choice, send data through internet service provider 1, and the cost is going to be 100 baht per megabyte that I send, or send through internet service provider 2 and it's going to be 50 baht per megabyte. Then if they care about financial costs, they'll choose internet service provider 2. So that's another way to choose the best path. Minimise the cost. Financial cost, that means here. Delay. These numbers could represent delay, for example, in milliseconds. Assuming you have fixed size packets, say 1,000 bytes for every packet, then we may be able to calculate to send a packet across this link has a delay of 1 millisecond. That's a total of transmission and propagation delay, possibly also processing delays. If we could calculate in our network the delays of sending data across each link, then we could say, choose the path from source to destination which minimises the delay. So again, it would be this path has a total delay of 1 millisecond plus 1 millisecond plus 2 milliseconds of 4 milliseconds to get from N1 to N6. So delay is another common metric for determining least cost path. Throughput or data rate may be another one, except it's not so obvious how we could deal with that. Maybe we have an example on one of the next slides. No, not yet. A simpler network, just for an example, node 1, 2, 3, 4. And another link here. And say all our links are bidirectional. If the characteristics of the links were known, so this node knows about the link that is connected to the next node. So this may be a node, both nodes in the same city, and there's a cable connecting them. And that link has some characteristics. For example, it may have a data rate, 10 megabits per second, and it may have a typical delay. The delay of sending a packet or the propagation delay across that link. And normally that information would be known to node 1. Because it's directly attached to that link, it knows the data rate because it must transmit across that link. And it could probably calculate or measure the delay across that link by sending some data, getting a response, and you can calculate the delay. Similar for the other links. They may have a rate and some delay associated with them. What have we got? So the characteristics of the links, if our cost, let's say our performance criteria, sometimes I'll use the word metric, performance criteria or metric. A metric is the thing that we use to measure the performance. If it is delay, what's the least cost path from, or what path do we choose from 1 to 4? Which path are we going to choose? 1 to 4? 1, 2, 3, 4. Okay. Delay is 1, 1, 2, and 5. If delay is our metric or performance criteria, then this path is better than this path. We only have 2 to choose from to keep it simple. This one has a delay of 1 plus 5 is 6. This path is 1 plus 1 plus 2 is 4. So we choose the path 1, 2, 3, 4. A total of 4 milliseconds delay. What if it was data rate? Which path? We've got one answer. Anyone else? Be careful. How do we use the data rate to calculate the performance of a path? Delay is simple because it's additive across the path. If I take 1 millisecond across the first link and then 1 millisecond across the second link, then across both of those links is just 1 plus 1 equals 2 milliseconds. That's additive. So to calculate the delay of the path, you just add up the delay of each link in the path. It's not like that for data rate. This link allows us to send at 10 megabits per second, this one at 5, this one at 10. So to deliver data from 1 to 4, I would be limited to 5 megabits per second. Because even though I can send at 10 to here, I cannot send any faster than 5 to here. So on average, I'm going to be limited by this link. We'd say this is the bottleneck link of that path from 1, 2, 3, 4. The minimum of the data rates limits the path data rate in this case. Because even we're sending fast here, it slows down across this link. So if we, on average, sending a lot of data, the rate from 1 to 4 via 2 and 3 is limited by this data rate of 5 megabits per second. Anyone have questions about that concept? This is not about delay, it's a rate. You are limited by the minimum of those rates. Yeah?
Number 2 and number 3 are 5 megabit per second. Mean 1 to 2 is also 5.
The data rate of this link is 10, the data rate of this link is 5, but let's say I have to send a lot of data from 1 to 4 along this path. Even though I can send my data at 10 megabits per second to here, that's going to arrive and queue up and can only be sent across the next path at 5 megabits per second. So overall, let's look at this link. If I can send at 5 megabits per second from 2 to 3, even though my data rate is 10 here, I'm not going to send any faster than 5. Because data is coming into 3 at 5 megabits per second. On average, I'm going to be sending half of the time and then sending nothing for half of the time. That is, it's coming in at 5 megabits per second. I transmit, let's say we had 1 megabyte of data. We transmitted that 1 megabyte at 5 megabits per second to 3. we can transmit that 1 megabyte from 3 to 4 in half the time at 10 megabits per second, but then we're transmitting nothing. So we're limited by this rate. Even though we can send faster on these two links, over a long period of time, the average is going to be limited by that 5 megabits per second. Similar concept if you put water through pipes. You're always going to be, if you've got a sequence of pipes, some are thick or wide pipes, can carry a lot of water per second, and some are very thin and carry less water. From source to destination, you're limited by that thin pipe over a long period of time. In this path, we have 15 and 10. The bottleneck link is this link. We're limited by this link in the second path. Therefore, we should choose the path 1, 2, 4. Which has a minimum data rate of 10 megabits per second. So you need to be careful that the metric that's used is not so obvious as to how to use that to find the best path. Or it's not always additive, like delay is. In practice, what's normally done if we use data rate or throughput is take, let's say if the maximum, let's try, if the maximum data rate in our network is, say, 20 megabits per second, the maximum possible data rate, I know this one's 15, 10, 5, 10, maybe there are other links, and the maximum is 20, what we can do is say, okay, take the data rate, what do we do? Take the maximum and divide by the data rate. So maximum divided by the data rate gives us 2 along this link. 20 divided by 10. On this link, 20 divided by 15 is what? 4 over 3. Or 1 1/3, 1.33 for this link. For this link, 20 divided by 5 gives us 4. And this link, 20 divided by 2, by 10 gives us 2. Now we can use these numbers. This link has a cost of 2 units, where the cost is calculated from this maximum number divided by the actual data rate. Cost of 2, 4 and 2. This has a cost of 1.33. Now we can do the normal approach of consider the additive cost. This path has a total cost of 2 plus 1.33, 3.33. This path, total cost of 2 plus 4 plus 2 is 8. Least cost path, 1, 2, 4. So what I did is that if we want to use data rate or throughput as the metric, but if we want to treat the network as this style of network where we allocate numbers to links indicating the cost and simply find the path with the least additive cost, then one way to do it when we use data rate is take some arbitrary or some maximum value and assign a cost based on the maximum divided by the actual. Really, and that's a way to use the additive cost across the path. That's not the point that we're trying to make here. That's just illustrating how we could use data rate. The point we're trying to make here is that we have different metrics. And depending on the metric, you may need to modify it to be able to use it as a cost on a link where we have an additive cost to give the least cost path. Number of hops is additive. That is, if one link has a hop of 1, a path with 2 links has a cost of 2 hops. Financial cost is additive normally. If it costs me 1,000 baht for the first link and 2,000 for the second link, the total cost is 3,000. Delay is additive. If a delay of 1 millisecond and then 2 milliseconds, total delay is 3 milliseconds. Throughput or data rate is not additive. In fact, we look at what is the minimum of all the values across a particular path. So we need to transform that somehow to make it into an additive value. That's all. So we may need to modify these values to make them work with our algorithms. We may use things which are not so obvious to measure to find the best path. Let's consider you have a company and you have operations across the world and you do business, and it's a law of your country or it's a principle of your company not to send data through a particular country in the world because of confidentiality reasons, for security reasons. Make sure your data never goes through country X because you don't trust them. Then that could be used as a routing metric. You need to choose a route that takes your data from source to destination, but it doesn't go through the nodes in that country. So it can be more complex than even these criteria. And finally, it can be a combination of those criteria. We can take into account both values. So we can apply some mathematics to combine them together, get some weighted average or weighted summation of these two to assign some cost. So it gets more complex than what we've gone through in the examples. They are performance criteria examples. When do we choose the best path? 2 basic approaches. If we're using datagram packet switching, we can choose based on each packet. That is, I have a packet to send from source A to destination B, choose a path, send that packet along the path. The next packet I have to send from A to B, choose a path again, possibly a different path. Send a packet across that path. So we could make decisions as to when to choose the path every packet that we need to send. If we're using virtual circuit packet switching, normally what we'd do is choose a path for the entire duration of that circuit. Remember with the virtual circuit from last week, we establish a circuit or a connection from source to destination. And then we send our data along that connection. Well, when we establish the connection, we should choose the least cost path, and all our data will go along that. So the time at which we decide what is the least cost path may vary depending on different algorithms, different approaches. When do you choose your path to drive into Bangkok? Well, maybe when you get in the car, you decide today, I'm going to take this path. Do you use the same path tomorrow? I choose a path to drive into Bangkok based upon minimal cost, minimal distance. And then tomorrow I get in my car to drive the same source, same destination. Do I use the same path? Okay, someone said yes. What about next week? Do you use the same path? What about next year? What about in 10 years' time? Things may change in the network over time. Maybe tomorrow I may use the same path because I expect nothing would have been changed along the roads between today and tomorrow. But maybe next week I'd like to choose or recalculate the path because maybe in the duration of 1 week there may be some roadworks or maybe one of the roadworks has been completed, so I'd recalculate the path. So we need to recalculate what is the best path on a regular basis because the network conditions may change. 1 hour later, the delay on this link, actually that's a bad example because that one was already small. Oh no, that's okay. The delay was 1 millisecond. Maybe 1 hour later it goes up to 15 milliseconds. If I'm still sending my data along this path, so initially with delay I chose 1, 2, 3, 4. I send all my data along that path. But the network conditions change. The delay on this path goes up. Maybe there's congestion at one of these nodes, a lot of traffic. It goes up to 15 milliseconds. If I keep sending my data along this path, I'm actually sending it on a suboptimal path. Because when this delay went up, this path became the best path. So what I should do is regularly recalculate the least cost path. So I get an up-to-date measure of the least cost path. We'll see approaches for doing that in a moment. What else do we do? Who decides on the path? We have a network. If I'm the person who built this network, I could decide upon the path and program it into these devices such that data will take a particular path. That would be a centralized approach. There's one central node that makes the decision. Or each node involved, nodes 1, 2 and 3, somehow work together to calculate the least cost path, a distributed approach. Or maybe the source node chooses a path. The originating source chooses a path and sends the data across that. So there are three basic approaches as to who makes the decision or where is the decision made. We'll see some examples of that in our subsequent routing strategies. And coming back, when I choose to drive into Bangkok, I need regular updates of where is the traffic jam, where are the roadworks. When I choose to route from 1 to 4, I need regular updates of what are the delays across the links. What are the nodes in the network? Have some nodes disappeared? Maybe this node has been down for 1 hour due to maintenance. Therefore, I need an update about that information. Which nodes give me this information? Which nodes are the source of this information? And how often do they give me this information? How often do I get updates? Some different approaches. None here means that there are no nodes that give me any information. I make a decision on the least cost path without any information about the network whatsoever. It doesn't seem possible, but we'll see how it can be applied in a very simple routing protocol. Local means this node makes a decision as to what path to take based only on information available at this node. This node knows nothing about these links. It knows nothing about this link, or this link. Node 1 should know about this link because it has a cable attached into this node. It knows what is the data rate and normally can calculate what is the delay. So we say local information is the information that this node only knows. Adjacent nodes. That is, this node knows information about this link plus its neighbour's links. Node 1 knows the data rate here is 10 and the data rate of its neighbour, 2, is 5 and 15. The more information we know, the more likely we'll choose the best path. Another approach is that node 1 knows about the information of that status across a particular path, and the best case is that the node knows about all the links and all the nodes in the network. It knows all the information about the network at that point in time. With more information, we can choose the better path. But we require some mechanisms to gather that information. Same when you chose how to drive into Bangkok. Some people said avoid the congestion, avoid the traffic jams. you need some mechanism to find out where is the traffic jam. Maybe you need to listen to the radio or ask your friends. That involves some overhead. So there's some trade-off involved there. How often do we get updates? Continuous means that we always know the value. Node 1 always knows the data rate of its link. If this link changes to 5 megabits per second, Node 1 knows that immediately. Periodic, every 1 minute, Node 2 tells Node 1 that its link to Node 3 has a delay of X milliseconds. So it gives us Node 2 sends an update to Node 1, say every 1 minute. This is the status of my links. And as things change in the network, every 1 minute, Node 1 will learn about those changes. Maybe there's a major change. When it says major load change, it means the amount of traffic going through a particular link changes. Although we measured data rate here, if it was a measure of throughput, this was 15, and maybe it drops down to 10 megabits per second. Maybe that triggers Node 2 to tell Node 1, the throughput has dropped. Update your information. So a major change in the network or a topology change. This node disappears. The node is turned off, it fails, something goes wrong. Node 2 should tell Node 1 there's no longer a path from 2 to 3 to 4. And then Node 1 would recalculate the new least cost path from 1 to 4, which will simply be 1, 2 and 4. So there are different criteria for measuring best path, different times and places where we calculate the least cost path, and different sources of information and mechanisms for getting updates as to how do we calculate the least cost path. Let's see some of them in place by looking at very general approaches for routing strategies. We'll just get through, I think, one of them today. The first strategy is fixed routing, where what we do when we build the network, we calculate the least cost paths when we start the network, we program that information into the nodes, and those paths stay as they are during the operation of the network. They don't change over time. As a result, the source or path from one source to one destination will always be the same. It will not change over time. So if the person who builds the network, if it's a company, they know about the topology of the network. They know the links because they put them in place. They know the costs of each of the links. So they can calculate the least cost paths. They can use algorithms for calculating them. Dijkstra, Bellman, Ford are two examples. There are others. They will calculate, we can use computer software to calculate the best paths. And then the path that we calculate is fixed for the duration of the network. It doesn't change. Unless there's a major change in the network topology. Maybe some nodes are turned off, then we may update. But the routes are fixed, so even if the amount of traffic going through the network changes, we do not change the path. So in our example, we had one example where the delay went from 1 millisecond to 15 milliseconds. Maybe that happened in just a matter of seconds or minutes. And it's at 15 milliseconds for 2 minutes. During those 2 minutes, this path is better than this one. With fixed routing, we would not use this better path. If we chose at the start the path from 1 to 4 is 1, 2, 3, 4, because of the delay was initially 1 millisecond, we calculate the least cost path based on delay. From 1, 2, 3, 4, or from 1 to 4, send on 1, 2, 3, 4. We're sending our data along this path. With fixed routing, we always send our data along this path. Even if this goes up to 15 milliseconds, we keep sending along this path. We don't try to adapt. It means that we'll use a suboptimal path, but it means it's very simple. We just calculate the routes at the start of the network operation and leave them. We don't need to get any updates. It makes the process simple, but means we use suboptimal paths, and that's a problem sometimes. We cannot respond to changes in the amount of data going through the network, changes in the performance of the network. So if there's an overload here with fixed routing, we still keep going through this path, which is not desirable in a number of cases. The advantage is it's simple. We calculate or assign the routes at the start and then do nothing in terms of routing. The disadvantage is it's not flexible. When the network is running, there may be regular changes in the amount of traffic being sent, changes in the delay and the throughput through the links. With fixed routing, it doesn't care about that. So the disadvantage, it doesn't consider these changes and therefore can choose, what do we say? Well, we don't choose the best routes, or we don't use the best routes all the time. We use suboptimal paths. We have 10 minutes left. First, to illustrate some of this. How many least cost paths are there? This network is the same as on one of the previous slides. How many least cost paths in this network? Calculate that. Calculate it and write it down on your slide. The first one, how many least cost paths are there? In fact, previously we calculated one of them. It's up on the board here. This is one of the least cost paths. From N1 to N6 was N4, 5 to 6. This is one of them. How many in total? If I need to write them all down, how many am I going to write down here? Anyone else got a better answer? How many nodes in the network? How many nodes in our network? 6 nodes. So the paths, we need to have paths between any pair of nodes. Node 1 needs to have a path to node 2, node 1 to node 3, node 1 to node 4, node 1 to node 6. How many there? Node 1 to 2, to 3, to 4, to 5 and 6. Gives us 5 paths. So node 1 should have 5 paths to all the other 5 nodes, and same for the other nodes. Node 2 needs a path to node 1, node 3, node 4, node 5, node 6. So node 2 needs 5 paths, node 3 needs 5 paths, we need a total of 30. With 6 nodes, we need paths between any pair, and there are 30 pairs there. 1 node to the 5 other nodes, and each node needs a similar 5 paths. Calculate them. Okay, we've calculated one. You could calculate the others. It would take you some time to calculate all 30. Path from What have we got? I don't know the answers. Node 1, node 6 to node 1. Again, you just need to inspect this simple network. 6 to 1, which of these gives the best path? This one's 4 plus 1 plus 7 is 12. Can we get better? 8 plus 6, 8 plus 3 plus 1. I don't think we'll get better than that one. So you'd need to inspect all possible paths. 8 plus 8 is 16, 12, 8, 9, this is going to be longer, 4, 5, 11, 5, 8. I think you will not get less than 12 in that case. There may be one with equal number. Node 4. And you can go through all the different pairs and calculate N1 to N3, N5 to N2, and all of them. Of course, you'll use a computer program to do that for you. Is a path less than 12? I hope so. Is it? What is it?
From N4 go to N2.
Yes, good. I wanted one, but I couldn't find it. N6 to N5 to N4 to N2 to N1. Nine. In different directions, we may have different paths. That was the point that this one makes. To go from N1 to N6, this path, but N6 to N1, this path. So we need to calculate in both directions. It's not simple in the opposite direction because our links may be different costs in each direction in general.
Actually, it's
10. I'll trust you. So we use in general for a network, we can use an algorithm to calculate that for us. Because as the network gets larger, it becomes a more complex task. Now, consider the first path, N1 to N6. We know the path. What's the least cost path from N4 to N6? In fact, we can ignore this because it's, although it's correct, it's not the point right now that we need. N4 to N6, if we know the least cost path from N1 to N6 is 1, 4, 5, 6, that it implies immediately, without looking at that the least cost path from N4 to N6 is this segment, N4, N5, N6. And the cost we need to look there to remember is what? 3. The point here is that if we know this path, then from this we can determine the path, the least cost path from N4 to N6. If there was a path from N4 to N6 that was not this, and that was a lower cost, if there was a path from N4 to N6 that went through other nodes which had a cost lower than 3, had a cost of 2 for example, then that means that the path from N1 to N6 would contain that lower cost path. This is a segment of the entire path, and if this is true, then immediately implies that the least cost path from N4 to N6 is this segment. And similar, from N5 to N6 is N5 direct to N6. So that's the first point, that because the costs of the paths are additive, we can make those implications about the segments of the paths. If there was a path from N5, although we know that there's not, if there was a path from N5 to N6 which went through some other node, N5, NX, N6, and it had a lower cost than this one, then that means from N4 to N6 would be N4, N5, NX, N6. And it means from N1 to N6 would be N1, N4, N5, NX, N6. But because we know this is true, then immediately we know this is true and this is true. This cannot be true. This cannot be the least cost path, that is. Or there cannot be another lower cost path. Now, the last thing for today, we need to store these paths in the nodes. So when node 1 has data to send to node 6, it looks in the storage and says, okay, to send to node 6, I send on the path node 1, I send to node 4, and then to node 5, and then to node 6. So we need to store that. This implication means all we need to store is the next node in the path. Node 1 stores the next node, so node 1 to reach node 6 stores the next node is node 4. Node 4 to node 6, node 4 needs to know that the next node is node 5. And from node 5 to node 6, it stores the next node is node 6. So what we need is to store the path from one source to one destination. But in fact, we don't need to store the entire path. What we do is we calculate the entire path, assuming the other nodes calculate the least cost paths as well. We only need to store the next node in the path. Because if node 1 sends to node 4, destined to node 6, node 4 to reach node 6 will send to node 5. Node 5 to reach node 6 will send to node 6. And we'll follow the path 1, 4, 5, 6, which was our desired path. So when we store this information in our devices, in the switching nodes, and even in our end stations, in fact, we don't need to store the entire path from 1 to 6. We only need to store the next node. From node 1's perspective, the next node is 4. From 4's perspective, the next node is 5. And from 5's perspective, the next node is 6. It cuts down on the storage requirements and in fact makes it simpler for updating this information as the network changes. We've run out of time for today. What we'll do tomorrow is illustrate that by looking at routing tables. Explain how a routing table stores this information.